Somewhere in your house there is probably a puzzle book, and inside it a grid of numbers you filled in on a slow afternoon. Take a finished one. Every square correct, every rule satisfied. Now find the square that came first. You cannot, and not because the answer is hidden, but because a finished puzzle does not have a first square. The order was something you brought to it. It was never in the grid. For a few years now, a small group of physicists and philosophers have been arguing that the universe is far more like that grid than like the machine we have always imagined, grinding the present into the future. If they are right, the flaw in our understanding of time is not in our clocks, it is in the shape of the story. So what are you doing in this moment if nothing is being worked out? Settle in and let the room go quiet around you. Subscribe if you haven't already, and stick around, because tonight ends somewhere I did not expect, with the word because turning out to belong to you rather than to the universe. Let's begin. Part 1. The assumption you have never examined. There is a sentence hiding underneath almost everything you have ever been told about physics, and almost nobody says it out loud, because almost nobody notices it is there. The sentence is this: the universe starts somewhere, and then it works out what happens next. That is it. That is the whole assumption. It sounds so obvious that reading it feels like a waste of your evening. Of course the universe works out what happens next. What else could it possibly do? But I want you to sit with it for a moment, because in the last several years a small group of physicists and philosophers of physics have started saying, carefully and in peer-reviewed journals, that this sentence may be the single largest mistake in our understanding of time. Not a small correction, not a refinement at the 10th decimal place, a mistake in the shape of the story itself. Think about how you were taught to do physics, if you were ever taught any. You're given a ball. You're given where it is right now, and how fast it is going right now, and in which direction. Then you're given a law, and the law is a machine. You feed the present into one end of the machine, and a moment later comes out of the other. Then you feed that moment back in, and you get the moment after. And you keep turning the handle, and out of the turning comes a trajectory, a curve through the air, a future. Isaac Newton gave us the first great version of that machine in the 1680s. Force equals mass times acceleration. It is not really a statement about the world so much as it is a set of instructions for grinding the present into the future. And for 2.5 centuries it worked so well that nobody had any reason to ask whether the instructions were describing the universe or describing us. Then quantum mechanics arrived, and it changed almost everything about physics except this. The Schrödinger equation, written in 1926, looks nothing like Newton's laws on the page. It deals in waves of possibility rather than solid little objects with definite positions. It replaced certainty with probability and made the world a great deal stranger than anyone had bargained for. But look at the shape of it. You put in the state of a system now. The equation tells you how that state changes. You turn the handle and out comes the state a moment later. Different clothing entirely. Same machine underneath. Every computer simulation ever run has this shape too, because a computer has no other way to work. When a weather model tells you it will rain on Thursday, it is taking the atmosphere as it is this morning, applying rules, stepping forward a few minutes, and doing that again several million times. When engineers plot a spacecraft's path to a moon of Saturn, they are doing the same thing with gravity instead of air pressure. When cosmologists grow a virtual universe inside a supercomputer, watching dark matter clump and galaxies condense out of the murk, they start with a smooth early state, and they let the machine grind. And because that is how we calculate, it is also, quietly, how we imagine. Ask almost anyone to picture the beginning of the universe and they will picture a start button. There is a flash, and then the universe is running, and it has been running ever since, and everything that exists right now is the output of a process that has been chewing forward for 13.8 billion years. That is not a fringe picture. That is the picture nearly everyone carries, including nearly every scientist, and it feels less like a theory than like a description of the obvious. The most honest statement of it was written in 1814 by the French mathematician Pierre-Simon Laplace, and it is worth hearing because of how naked it is. Imagine, Laplace said, an intelligence that knew the position and momentum of every particle in the universe at a single instant, and knew all the laws. For such an intelligence nothing would be uncertain. The entire future, and the entire past would lie open in front of it like a book already written. That imagined intelligence has been called Laplace's demon ever since, and notice what the demon is actually doing in that story. The demon is running a simulation. It takes a slice of the universe and it turns the handle. I want to draw your attention to how deeply this picture has shaped things that feel like they have nothing to do with it at all. It has shaped what counts as an explanation. When a physicist explains why something happened, the explanation nearly always takes the form of a story in which earlier things produce later things. This particle was here, so that detector clicked. The star ran out of fuel, so the core collapsed. We do not think of that as a choice. We think of it as what explaining means. It has shaped what counts as a mystery. Quantum nonlocality, the business you have heard described as spooky action at a distance, the strange coordination between particles separated by a room or by a continent, is treated as one of the great scandals of modern physics, and it is genuinely peculiar. But part of the reason it registers as a scandal, rather than as a curious fact, is that in the step-by-step picture correlation between distant events demands that something must have travelled between them. If nothing travelled, how did the far side know? That question only has teeth if you have already assumed the universe works by passing things forward, and it has shaped what counts as a solution. For decades, a great deal of very serious work in quantum foundations has been aimed at recovering a causal account of quantum phenomena, either an ordinary classical story about one thing causing another, or some new quantum notion of causation that would let us tell a similar story in stranger language. That research program is enormous. It is well-funded and well-populated and full of clever people, and a small number of those people have begun to suspect that the entire program is trying to force the universe into a shape it does not have. Here is the suspicion stated plainly, and then I will spend the rest of tonight showing you where it comes from. The suspicion is that time evolution is not a feature of the universe. It is a feature of the method. It is how we solve problems, because we are the kind of creature that has to solve problems one step at a time, with a pencil or a processor, working from the known toward the unknown. We built a technique in our own image. The technique worked beautifully, and then we forgot it was a technique and started treating it as a description of what the world is doing when nobody is calculating. In 2012, a physicist named Ken Wharton at San Jose State University wrote a short essay with a title that functions as a flag planted in the ground. He called it "The Universe is Not a Computer." His argument was that we took the computational picture too literally, that this was an anthropocentric assumption rather than a discovery, and that it had steered our physical models into a corner they never had to enter. The essay won third prize in a contest run by an institute that exists more or less, because these questions are considered too foundational to attract ordinary grant money, which tells you something about how the field regarded the question at the time. Nobody had to take that seriously. It was an essay, and essays are cheap. But over the following decade, the argument stopped being an essay and started being a research program, with formal papers in Foundations of Physics and Entropy and the Proceedings of the Royal Society, and with a specific accusation attached to it, that the assumption we have been discussing is not merely unexamined but actively holding physics back, that it has been quietly deciding the answers to questions before anyone asks them, and the person who has pressed that accusation hardest is a philosopher of physics with a doctorate in physics, working in a small institute in Southern California, and she has an image for what the universe might be instead. It is not a machine. It is not a program running forward from a start button. It is something you have almost certainly held in your hands, on a train, or in a waiting room, or on a slow Sunday morning, without ever once thinking of it as a model of reality. It is a puzzle. And the strange thing about a puzzle, the thing that is about to take the floor out from under this entire picture, is that a puzzle does not have a beginning. Part 2. The completed puzzle. I want you to picture a finished Sudoku grid. 9 rows, 9 columns, 9 little boxes inside the big square, every cell filled in, all of it correct. Now let me ask you a question that sounds like nothing and is not. Which cell came first? Go across the grid in your mind. Look at the top left corner, then the middle, then the number sitting quietly in the bottom right. Try to find the one that came before the others. Try to find the cell that caused the cell beside it, the way a shove causes a fall. You cannot do it, and I want to be precise about why, because the reason is the whole point. It is not that the answer is hidden. It is not that you would need more information, or a faster brain, or a record of the order the solver filled it in. It is that the completed grid does not contain the kind of thing your question is asking about. The question has no purchase. A finished Sudoku puzzle simply does not have a first cell, in the same way that a circle does not have a corner. Now look at what the rules of Sudoku actually do, because this is where it gets interesting. The rules do not say start in the upper left and work rightward. The rules do not say anything about starting at all. What they say is that every row must contain each number once, and every column must contain each number once, and every box must contain each number once. That is it. Those rules apply to the entire grid, all at once, and their only job is to sort every possible filled-in grid into two piles, valid and invalid. There is no direction of solution written into the rules. The direction comes from you. You solve a puzzle in an order because you are a person with a pencil and a limited amount of attention, working from what you already know toward what you do not. That order is a fact about how you solve. It is not a fact about the puzzle. I would like you to hold on to a phrase because we are going to come back to it several times tonight, and by the end it will not mean quite what it means now. Some rules push, some rules permit. Newton's second law pushes, give it a present and it produces a future. The rules of Sudoku permit. They do not produce anything at all. They simply say yes or no to whole patterns. Those are two genuinely different kinds of law, not two descriptions of the same kind of law, two different mathematical animals. And the claim at the center of tonight, the claim that gives this video its title, is that the laws of nature might be the second kind, and that physics has spent 300 years assuming, without ever really arguing for it, that they are the first. The person who has made that case most forcefully is Emily Adlam, a philosopher of physics at Chapman University in Southern California, where she works in an institute devoted to the foundations of quantum theory. Her background matters here, so let me give it to you. She studied physics and philosophy together as an undergraduate. Her doctorate is in physics, not philosophy. She has said that for a long time it was genuinely a toss-up which she would end up being, a physicist working on foundations or a philosopher, and that the work she actually wanted to do finally felt as though it lived more comfortably on the philosophy side. So when she tells physics it has a bad habit, she is not shouting from the pavement outside. She trained in the building. Her image for what the universe might be is the one you have been holding for the last few minutes. She calls it, informally, the Sudoku universe. The rules of Sudoku, she points out, do not tell you to start on the left and move toward the right. What they do is constrain the whole grid and tell you whether an entire solution is valid or invalid. Perhaps, she says, the laws of nature work like that, and not like time evolution. Take that seriously for a moment and notice what it does to the picture from a few minutes ago. There is no initial state being fed into a machine. There is no machine. There is a space of possible whole histories, every complete four-dimensional pattern of everything, from beginning to end, all of it at once, and the laws are constraints that go through that space and sort it. Most of those patterns are ruled out. A tiny number are permitted, and the one we are living in is one of the permitted ones. Nothing is being computed. Nothing is being produced. The universe is not working anything out. There is a subtlety inside this that is worth having, because it is the difference between a mildly interesting idea and a genuinely disorienting one. One kind of all-at-once model is fairly familiar to physicists already. You fix the conditions at the start and the conditions at the end, and you ask the laws to fill in the middle. That is a boundary value problem, and boundary value problems turn up in perfectly ordinary physics all the time. But Adlam's preferred version is more general than that, and stranger. On her picture, the laws determine the whole history at once, and it will often be the case that you can fix any state anywhere along that history, and that will be enough to fix all the rest. It could be the first moment, it could be the last, it could be a Tuesday somewhere in the middle for no particular reason. No moment is privileged, not the beginning, not now. The history as a whole is what the laws select, and any slice of it is as good a handle as any other. She's careful about one thing here, and I want to preserve the care, because it is the difference between a research program and a slogan. Consistency alone is probably not enough. You might hope that the entire universe could be derived from the single requirement that it not contradict itself, and that would be a very tidy result. But Adlam says plainly that she does not know how to get the actual laws we observe out of pure consistency conditions. It would be neat if it could be done. It probably needs more than that. Some further constraints that pick out the specific kinds of laws we happen to see. Now, if this were only a philosophical preference, a matter of which picture you find prettier, I would not be spending 2 hours of your night on it. So let me point out something that tends to surprise people, including people who have taken a fair amount of physics. We already have all-at-once formulations. We have had them for centuries. We just translate them back into the pushing picture out of habit. Stretch a soap film across a bent wire loop, and it finds the shape with the least possible area, instantly, with no computation and no stepping. Hang a chain between two posts and it settles into a curve, the catenary, that minimizes its energy across the entire length of the chain considered as a whole. Nothing crawls along the chain deciding. The shape is a global solution to a global condition. Light does something similar, and it bothered people enormously when it was noticed. In the 1600s, Pierre de Fermat pointed out that light travelling between 2 points, bending as it passes from air into water, takes the path that requires the least time. That is a beautiful result, and it made his contemporaries deeply uneasy, for a reason you can probably feel yourself. To take the quickest path, the light appears to need to know at the outset where it is going and what lies ahead. It is a rule about the whole journey, stated as a property of the journey, and it does not decompose neatly into a series of little decisions made in sequence. That style of reasoning grew into the most elegant formulations physics has. They are called action principles, and in them you do not step a system forward at all. You consider entire paths, evaluate a quantity across the whole of each one, and the path nature takes is the one that makes that quantity stationary. Classical mechanics can be written this way, so can electromagnetism, so in a certain sense can quantum theory in the formulation Richard Feynman built, where you add together contributions from every possible path a particle could take between 2 points. This is Wharton's actual technical argument underneath the provocative title. Classical computation, he points out, is essentially Newtonian iterative calculation. Grind, step, grind, step. But the deepest descriptions we have of the physical world are least action descriptions, evaluated across whole histories. So the universe is not a computer in a very specific and defensible sense. Its most elegant description is not an iteration. We have had these formulations in our hands for 200 years, and what have we done with them? We have taught generations of students to admire them briefly, derive the equations of motion from them, and then go back to stepping the system forward, because stepping forward is how you get a number out by Thursday, which is fine. That is what techniques are for. The trouble only starts when you stop noticing that you are using one. Now, everything I have told you so far is elegant, and elegance proves nothing. If this were only about which picture is nicer, it would be an argument about taste, and physics has better things to do than argue about taste. But it is not about taste. Because starting in 1964, and accelerating hard from the 1980s onward, the universe began handing physicists a specific piece of evidence that does not sit comfortably in the pushing picture at all. Evidence so uncomfortable that it has been called the strangest result in the history of science, and so well confirmed that it collected a Nobel Prize 4 years ago. And the reason it is strange, as you're about to see, may be almost entirely our fault. Part 3. The place the flaw first showed. The evidence begins with a quiet man from Northern Ireland who worked at a particle physics laboratory near Geneva and did the most important thinking of his life in his spare time, because it was not the kind of thinking his employers were paying for. John Stuart Bell was an accelerator physicist by trade. Foundations of quantum mechanics was, in the 1960s, considered slightly disreputable, the sort of thing you might dabble in once you had a permanent position, and could afford the reputational damage. Bell dabbled. And in 1964 he published a short paper that a number of people have since called the most profound discovery in the history of science, which is a large claim, and which I think survives contact with the details. To see what he did, you need to know what he was responding to. In 1935, Albert Einstein, Boris Podolsky and Nathan Rosen had published an argument aimed at showing that quantum mechanics was incomplete. Their reasoning ran roughly like this. Prepare two particles together so that their properties are linked, then separate them. Measure one, and you immediately know something about the other, no matter how far away it is. Either the distant particle changed the instant you measured yours, which Einstein found intolerable, since nothing should be able to reach across space that quickly, or the distant particle had its properties all along, and quantum mechanics simply fails to describe them. Einstein preferred the second option. There must be extra facts, he thought, that the theory is not telling us. Hidden variables in the jargon. That is a very reasonable position, and it is worth noticing that it is also the ordinary position we take about everything else in life. Suppose I take a pair of shoes, Put the left one in one box and the right one in another, seal both, and mail one to you and one to a friend in Auckland. You open yours and find the left shoe. In that instant you know, with certainty, that a box on the other side of the planet contains a right shoe. Nothing travelled, nothing spooky happened. The shoes were always what they were. You simply learned which was which. Bell himself made this point with a story about a colleague named Bertelmann, who always wore socks of two different colours, so that seeing one pink sock told you instantly, at any distance, that the other was not pink. That is what we mean by a common cause. Two distant things are correlated because something in their shared past made them that way. Every ordinary correlation in your life works like this, and it is the backbone of how we explain the world. Bell's insight was to ask a question nobody had thought to ask, and it is the kind of question that changes a field. He asked, if every correlation is explained by a common cause of this sort, if the shoes were always in the boxes, is there a limit to how strongly two distant measurements can agree? There is. That is the theorem. Bell showed that any explanation in which the outcomes were fixed in advance by shared local factors imposes a ceiling on the strength of the correlations you can get once you start measuring the two particles along different, freely chosen directions and comparing the statistics over many runs. The ceiling is a mathematical inequality. It is not a claim about quantum mechanics specifically. It applies to any theory of that shape, including ones nobody has thought of yet. And then Bell showed that quantum mechanics predicts violations of that ceiling, which meant the argument was no longer philosophy. It was an experiment waiting to be built. It took time to build it. Through the 1970s, John Clauser and others ran early versions with growing confidence. In 1981 and 1982, Alain Aspect and his colleagues in Paris ran the tests that convinced most of the field, using switches that changed the measurement settings, while the light was already in flight so that no signal travelling at ordinary speeds could have carried word ahead. The results violated Bell's ceiling, and they matched quantum mechanics. Skeptics spent the following 30 years hunting for loopholes, clever ways the universe might have cheated, by hiding correlations in the detector efficiencies, or by sneaking information between the measurement stations. In 2015, a team led by Ronald Hansen in Delft closed the two most important loopholes at the same time, using entangled electron spins in diamond crystals held in laboratories more than a kilometre apart across a university campus. In 2017, a Chinese satellite called Micius, led by Jianwei Pan, distributed entangled photon pairs to ground stations more than 1,200 kilometres apart, a separation roughly the length of the Italian peninsula, achieved with the entanglement intact. In 2022, the Nobel Prize in Physics went to Aspect, Clauser and Anton Zeilinger for this body of work, which is a satisfying ending for a topic that had been considered slightly embarrassing when Bell first touched it. So here is the finding, stated as carefully as I can. Quantum mechanics exhibits correlations that are too strong to be explained by any local common cause model. Ordinarily, when we see things correlated at a distance, we explain it by something they share in their past. Bell's theorem shows that this style of explanation cannot account for what quantum systems do. Now watch what happens next, because this is where the flaw first becomes visible if you know where to look. Faced with that result, the overwhelming instinct of the physics community was to ask, then what travelled? If the shoes were not in the boxes, something must have carried the news, and so the standard picture became a story about a wave function that collapses everywhere at once. Alice measures her particle in one place. In that instant, the global state of the world changes, everywhere, simultaneously, and that change conveys something across to Bob, wherever he is, and shapes what he finds when he measures. The nonlocality is spatial. The effect of what Alice does gets stuffed into the global state, which exists everywhere at the same time, and that is how the far side finds out. That picture is spooky. It is supposed to be spooky. It is spooky enough that Einstein used the word, and the word has stuck to it for 90 years, but notice the assumption doing the work. The reason the result feels like a scandal, rather than like an interesting structural fact about the world, is the demand that something must have travelled. And that demand is not something Bell proved. That demand is the time evolution picture wearing a costume. Go back to the completed grid. A Sudoku solution is absolutely stuffed with correlations. The number in one corner constrains the number in the far corner. Change one cell and the whole grid becomes invalid. Two cells on opposite sides of the puzzle, cells that never touch, are locked together in a way you can verify precisely. If you insisted on explaining that with a common cause, you would fail. There is no shared path between two cells of a puzzle. If you insisted that something must travel between them, you would spend your life looking for a messenger that does not exist. And yet nothing is wrong with the grid. Nothing spooky is happening in it at all. Correlation across the whole pattern, with nothing travelling and nothing produced, is simply what a global constraint looks like from the inside. I want to be scrupulous here, because this is the point where popular treatments start going wrong, and we are not going to. Nothing I have said means you can use any of this to send a message. There is a theorem, it is called no signalling, which guarantees that Alice's local results taken by themselves are completely unaffected by anything Bob does or chooses. He cannot make her instrument behave differently. Nobody can push information down this channel, because it is not a channel. We will come back to this, because it is the firewall that keeps every version of tonight's story honest. But leave that to one side for now, and sit with the shape of the argument. Bell's theorem tells us the world cannot be explained by little local facts propagating forward. We received that news and immediately tried to describe it using a global state propagating forward, which is the same assumption, only larger. Emily Adlam's position is that this was a choice, made almost invisibly, and that a different choice was available, and the reason almost nobody sees the alternative is not that it is subtle or hard. It is that our mathematics is written in a way that hides it. Because there are two ways for a correlation to be non-local. One of them is across space, and that is the one that made every documentary, every popular book, every headline for 60 years. The other one is across time. Almost nobody talks about it, and the argument I am about to show you says that if you accept the first one, and you accept Einstein's own theory of relativity, then you have already accepted the second. You simply have not noticed. Part 4. The half of non-locality nobody talks about. Let me set the two options side by side, because the difference between them is the hinge of this entire video. The first option is the one you know, spatial non-locality. Alice measures her particle in a laboratory in Vienna. At that instant, everywhere in the universe, the global quantum state changes. That change is present in Delhi and in Santiago, and out past the orbit of Neptune, all at once. And when Bob measures his particle, wherever he happens to be, the altered global state is what shapes his result. Something is transmitted in a manner of speaking. It is transmitted instantaneously and everywhere, which is odd. But the structure of the story is familiar. A change happens here, the world updates, and the update is what reaches there. The second option is stranger and quieter, and it barely appears in popular accounts at all. Temporal non-locality says that a non-local relationship does not have to be carried by the current state of the world. Alice performs her measurement at one time and place. Bob performs his at a later time somewhere else. And there is simply a direct relationship between the two events. A constraint requiring that Bob's outcome reflect Alice's choice in some way. With nothing in between doing the carrying. No global state updating. No wave sweeping outward. No messenger of any kind. A relationship that hops across time rather than crawling through it. If your immediate reaction is that this sounds worse, I understand. Give it a few minutes. Now I want to take you somewhere, because this next step is best felt rather than argued. Imagine two rooms, far apart, each holding one half of an entangled pair. In one room, Alice sets her detector and takes her reading. In the other room, Bob sets his and takes his. On the wall of each room is a clock, and by the reckoning of everyone standing still on the ground between them, the two readings happen in the same instant. Alice at 3 o'clock, Bob at 3 o'clock, simultaneous. Now leave the ground. Imagine yourself aboard a ship travelling past the whole arrangement at a good fraction of the speed of light. You're not doing anything to the experiment. You're not touching it, or heating it, or looking at it too hard. You're simply moving, and from where you sit the two events come apart. You watch Bob take his reading. Then, afterward, unmistakably afterward, you watch Alice take hers. In your accounting, Bob's measurement is the earlier event, not by a hair. By whatever margin your speed and the distance between the rooms decide, and if the rooms are far enough apart that margin can be seconds, hours, days. And here is what makes your stomach drop. There is no fact about who is wrong. Your account and the ground account are both correct. Relativity does not say one of you is confused. It says that for two events far enough apart in space and close enough together in time, events that no signal at light speed could bridge, what physicists call space-like separated, there is no such thing as their order. The order is not a hidden truth you both approximate. It genuinely is not there. Somebody else, moving differently again, will put them simultaneous. Somebody else will reverse them the other way. The flaw of before and after is not a flaw, it is on rollers, and nothing you did moved it. You just walked across the room, let that settle, and then take the last step, which is Adlam's. Suppose you believe in spatial nonlocality, the story where Alice's measurement reaches across space and shapes Bob's result at the same moment. Fine. Now change reference frames, which relativity says you are entitled to do, and which does not alter a single physical fact about the experiment. In your new frame, those two events are no longer simultaneous. Bob's outcome now lies in the future or in the past of Alice's action. And so the influence you were calling spatial, a reach across a gap in space at a shared instant, has become a reach across a gap in time. You did not add anything. You did not introduce a new mechanism. You changed the frame, which relativity insists is meaningless, and the non-locality quietly changed its species. Which means that if you take seriously what relativity says about the intimacy between space and time, and every working physicist does, because relativity is the most tested framework we have, it becomes very difficult indeed to maintain that non-locality is always spatial and never temporal. You cannot have the first without the second. The two are the same thing seen from different chairs. So why has essentially the entire field talked about one of them for 60 years and not the other? Adlam's answer is the thing I have been building toward all night, and it is unnervingly simple. It is because quantum mechanics is formulated as a time evolution theory. That is all. In the standard formulation, the fundamental object is a global state, and the fundamental operation is carrying that global state forward. Everything the theory knows, it knows in the form of a state at time. So if you go looking for a place to put non-locality inside that machinery, there is exactly one shelf available. You must put it in the global state, and you must have the global state change everywhere at once, because that is the only kind of change the formalism can express. The mathematics did not discover that non-locality is spatial. The mathematics had nowhere else to file it. I find this genuinely unsettling, and I want to say why in plain terms. We tend to imagine that our equations are neutral instruments, that we look at nature, write down what we see, and the notation simply records it. But notation has opinions. A formalism built around states at times will describe every phenomenon it meets as a story about states at times, because that is the only sentence it can form. And then, decades later, everyone in the field will be arguing about the meaning of the story, and nobody will be arguing about the grammar, because the grammar has become invisible. Adlam puts the flip side just as plainly. If you formulate quantum mechanics in a different way, as something other than a time evolution theory, then temporal non-locality becomes natural and compelling, and the spatial version stops being the obvious reading. It is not that one is right and the other wrong on the evidence. The evidence is the same evidence. The choice was made by the shape of the tool. There is a further embarrassment sitting inside the standard picture that is worth pausing on, because it shows the strain from another angle. The collapse everywhere at once story requires an at once. It requires a moment in which the global state changes across the whole universe. But we have just established that for space-like separated events there is no shared moment. Simultaneity is a matter of which chair you're sitting in. So in which frame does the wave function collapse? The theory does not say. Physicists have known about this awkwardness since the 1930s and have largely managed it by not looking directly at it, which is a technique I have used myself on several household repairs. Whereas a constraint has no such problem. A constraint on a whole history does not happen at a time. It does not need a moment to be true in. It relates events, and it is indifferent to how any particular observer slices them up. Think about the finished puzzle again. The rule that says this row contains each number once is not true at some particular hour of the afternoon. It is not waiting for anything. It is a fact about the whole arrangement, and no matter how you carve the grid into strips, or in what order you read them, the rule holds. That indifference is not a trick of presentation. It is the specific property that lets a constraint do the work a collapsing state was being asked to do, without ever needing to answer the question of when. So let me restate where we have arrived, because we have covered a lot of ground and I want it clean before we go further. Bell's theorem tells us the world's correlations cannot be built out of local facts fixed in the shared past. The standard response was to keep the forward-moving picture and make the moving thing global. Adlam's response is to notice that relativity turns that picture into a temporally non-local one anyway. that the only reason we did not see this was the shape of our own notation, and that if you are willing to give up the evolution story altogether, the whole business stops being spooky and starts being ordinary, because global constraints correlate distant things without transmission as a matter of course. It is what they do. It is the only thing they do. This is a serious claim, and by 2018 she was ready to make it in a serious place, in a journal called Entropy, in a paper with a title I have always thought was rather wonderful, Spooky Action at a Temporal Distance. But the title is not the part that made people sit up. The part that made people sit up was a single word she used to describe the assumption we have been circling all night, a word that is not really used in physics papers, because it is not a technical term, it is an accusation, a word that says the problem is no longer an oversight, and has become something closer to a belief that the field is protecting. She called it a dogma, and then she did something considerably more dangerous than name-calling. She took one of the most celebrated theorems of the last 20 years, a theorem people had built entire positions on, and showed that it had been quietly resting on the dogma the whole time. Part 5. The word dogma. Scientists do not usually call each other dogmatic in print. It is not done. The conventions of a physics paper are built to keep the temperature low. You write that a particular assumption may warrant further examination, or that certain approaches have received disproportionate attention, and everyone reading understands you are furious. So when a paper published in a peer-reviewed journal says that a widespread assumption has become a dogma, and that it is actively limiting progress in the field, that is not a turn of phrase. That is somebody deciding the polite version has not worked. The paper is Spooky Action at a Temporal Distance, published in Entropy in 2018. Adlam's argument in it begins with an observation about the last 60 years that is hard to dispute once it is pointed out. Since Bell's theorem, she notes, the physics community has come to take entirely seriously the possibility that the universe contains processes that are spatially non-local. That took decades, and it was painful, but it happened. There has been no comparable revolution with regard to temporally non-local processes, and her claim is that the unexamined assumption of temporal locality is holding the field back. The strong words need justifying, and she justifies them by pointing at the shape of ongoing work. In quantum foundations, it remains very common to be focused on giving causal accounts of things, either in classical terms or by moving to some quantum notion of causation in which you can still tell a story about one thing causing another thing causing another thing. Her assessment is blunt. That is not a good use of our efforts, because there are clear indications that this is not the structure physics actually has, and trying to force it into a causal structure is unlikely to be a good way of understanding it. So we should be precise about what temporal locality actually says, because it is the specific bolt she is trying to loosen. Temporal locality is the assumption that if a measurement result depends on something that happened earlier, then there must be something that travels between them, carrying the information from the earlier moment to the later one. Some carrier, some continuous chain of mediation running through the intervening time. Not necessarily anything you can see or catch. It might be a wave function, it might be a field configuration, it might be some hidden variable nobody has identified. But something, persisting, and doing the ferrying. Read that assumption again and notice how utterly reasonable it sounds. Of course, something carries it. What is the alternative? That the later event simply matches the earlier one with nothing in between doing any work. Yes, that is precisely the alternative. In a constraint picture, a relationship between two moments is a fact about the whole pattern, and patterns do not need couriers. Now, having stated the assumption, Adlam did something considerably sharper than complain about it. She went and found it hiding inside one of the most celebrated results of the century. The result is called the PBR theorem, after Matthew Pusey, Jonathan Barrett and Terry Rudolph, who published it in 2012. When it appeared, it was hailed in some quarters as the most important theorem in the foundations of quantum mechanics since Bell's, which is not a modest comparison. What it addresses is one of the oldest questions in the subject. Is the quantum state a real thing, or is it a description of what we know? That question has been argued since the 1920s. On one side, the quantum state, the wave function, is a genuine physical object, out there in the world, as real as a magnetic field. On the other side, it is a bookkeeping device, a summary of an observer's information about a system, which updates when the observer learns something, in the way that your beliefs about a coin update when you look at it. The second view has always been attractive because it makes the notorious collapse of the wave function completely unmysterious. Nothing physical collapses when you look at a coin. Your ignorance collapses. The PBR theorem attempts to close that door. It argues that in order to reproduce all the predictions of quantum mechanics, it must be the case that the quantum state is a real, objective thing, which travels through time conveying information from one moment to another. If that is right, the knowledge interpretation is dead, and a large family of comfortable positions dies with it. Emily Adlam read that theorem and had what I can only describe as the good kind of doubt. There is a phrase in physics folklore called the happiest thought. It comes from Einstein, who recalled that in 1907, sitting in the patent office in Bern, it occurred to him that a person in free fall does not feel their own weight, and that from this small domestic observation, the whole architecture of general relativity eventually unfolded. Asked whether she had ever had a happiest thought of her own, Adlam picked this moment. What struck her about the PBR theorem was that the entire argument was predicated on temporal locality. The proof assumes that if a measurement result depends on an earlier preparation, there must be something travelling between them carrying that information from one point to another. It assumes it so quietly that the assumption is not really flagged. It is not in the list of premises anyone was arguing about. It is in the grammar, and once you see it, the theorem's conclusion changes shape. Her published reading is that the theorem should really be glossed as a choice between two things, not as a proof of one. Either the quantum state is a real objective thing, or some quantum measurement results depend, in a temporally non-local way, on events at other times. That is what the mathematics actually establishes. The famous version, the one people built positions on, is what you get when you assume the second option is unthinkable and quietly delete it. I want to make sure the force of this lands, because it is a different kind of move from the one people usually make in these arguments. She did not find an error. There is no arithmetic mistake in the PBR theorem. She did not claim the result is false. What she did was show that a celebrated theorem proves less than everybody thought, because a premise nobody had written down was doing part of the lifting. The theorem is a fork in the road that had been presented as a wall, and the second path was invisible because the field had agreed, without discussing it, that paths of that kind do not exist. That is a genuinely uncomfortable thing to have pointed out to you, and the discomfort generalizes immediately, which is the real payload. If temporal locality was hiding inside that theorem, unexamined, how many other results of the last 100 years have it in them? How many arguments that feel like proofs about the world are partly proofs about the assumptions we brought? There is a small irony worth mentioning here, and it lives about 100 meters from Adlam's office. The institute she works in at Chapman University was co-founded by Yakir Aharonov, and Aharonov is one of the very few physicists of the last century who took the other path early and never left it. In 1964, with Peter Bergman and Joel Lebowitz, he proposed describing a quantum system using two states rather than one, a state evolving forward from how the system was prepared, and a second state evolving backward from how it was eventually found. Two boundaries, not one beginning. In 1988, with David Albert and Lev Vaidman, he introduced the measurable quantities that come out of that two-boundary picture, called weak values, which are used in laboratories today by people who have no interest whatsoever in philosophy and simply find them a useful tool. So the alternative was never actually absent from physics. It has been sitting in the literature for 60 years, in the work of a well-known physicist, occasionally winning arguments, and being politely regarded by the mainstream as an interesting formal curiosity rather than as a statement about how the world is put together. That is what a dogma looks like from the inside. It does not forbid the heresy, it just declines to notice that the heresy is an option. I am not going to tell you the answer is all of them, because I do not know, and neither does anybody else. That is rather the point. Nobody has gone through the literature with this specific torch. That is what Adlam means when she says the assumption is limiting progress. Not that it makes people stupid, but that it makes certain conclusions unreachable in advance, and you cannot notice a conclusion you were never able to consider. Now, if you have been listening carefully, there is a question forming, and I suspect it has been forming for a while. It usually arrives sounding something like this. Hang on. If a later measurement can depend on an earlier one without anything travelling, and if changing your reference frame can turn a spatial relation into a temporal one, are you telling me the future affects the past? That is exactly the right question, And I am going to answer it properly because this is the single place where this material gets stolen and turned into nonsense. There is an entire industry of people who take this corner of physics and sell it as evidence that you can reach backward and edit your own history. So let us go there carefully. The honest answer involves two different ideas that get lumped together under one word, and telling them apart is what separates a strange, defensible picture of the universe from a very old and very profitable lie. Part 6. Retrocausality without a traveller. The word retrocausality gets used for two completely different pictures, and nearly all the confusion in this area comes from that one collision. The first picture is the one everybody imagines. Something propagates backwards in time. It leaves a later moment, travels through the intervening interval in reverse, and arrives at an earlier moment carrying information. Call it dynamical retrocausality. Now, I want you to notice something about that picture that took me an embarrassingly long time to see. It is still the old assumption. It has a carrier, it has a path, it has continuous mediation through the intervening time. It is temporally local in exactly the sense we spent the last part dismantling. A story about something travelling between two moments, with the mediation doing the explanatory work. All that has changed is which way the traffic flows. You have kept the machine and reversed the handle. The second picture has no traveller at all. In the all-at-once version, there is simply a global constraint relating two events across time. The constraint applies to the whole history. Because it applies to the whole history, there is nothing for a carrier to do. No wave slides backward, no influence crawls anywhere. There are two events, and there is a rule that says patterns in which those two events fail to match are not permitted patterns. That is not the future affecting the past. That is a fact about the shape of a whole thing. Adlam is careful about the vocabulary here, and I want to preserve her care because it does real work. She uses the word retrocausality in this connection, she says, in a loose way, to connect what she is doing to more traditional discussions. But strictly speaking, she does not think what is going on is retrocausality at all, because she does not think there is causality in fundamental physics. Neither the forward direction nor the backward direction is truly causal. There is no causing happening down there in either sense, and so there is no such thing as causing in reverse. What she allows is this. If you step up to a more macroscopic view, and you write down a causal model in which a person intervenes on something, then from that standpoint you will get effects that look retrocausal. That is a real appearance, and it is worth describing. But at the fundamental level, none of it is causal, and she thinks you should say so plainly rather than dressing the constraint up in the clothes of a backwards-running cause. The historical relative of these ideas is worth meeting, because it shows the pressure toward the all-at-once picture happening in real time to somebody who did not set out to end up there. In 1986, a physicist named John Cramer proposed what he called the transactional interpretation of quantum mechanics. The idea is genuinely lovely. A quantum event is a handshake. The source sends out what Cramer called an offer wave, moving forward in time, and the eventual absorber sends back a confirmation wave, moving backward in time, and the transaction is completed when the two meet and agree. The picture has a pleasing symmetry, and it makes several quantum puzzles look much less strange, because you're no longer asking how a particle knew where to go. The destination was part of the arrangement from the start. The most famous objection came from the philosopher Tim Maudlin, and it is elegant in the way good objections are. It takes the picture at its word and then puts it in a situation it cannot survive. Maudlin's scenario involves an experiment in which a preliminary measurement taken partway through determines something about what the final measurement will be. Perhaps the setting of the second detector depends on what the first one found. Now the transactional story is in trouble, because that story is supposed to take a fixed initial condition and a fixed final condition and determine what happens in between. But in this arrangement, the final condition is not fixed independently. It is itself downstream of what happens in the middle. You have written a definition that eats its own tail, and you can construct cases where it produces a straightforward contradiction. Adlam's assessment is that the sophisticated versions of the transactional interpretation do escape this objection, but she is precise about how they escape it, and this is the part that matters. They escape it by moving away from the story in which there is a literal transaction taking place as a temporal process, a handshake occurring in time between waves that go out and come back, and moving toward an all-at-once picture in which the whole arrangement is atemporal and has to be understood as being fixed for consistency in that atemporal sense. In other words, the fix is to stop telling the story as a process, and she takes this as a general lesson. Resolving problems of this kind, both in the transactional interpretation and in retrocausal models more broadly, does seem to push you toward the all-at-once picture. Not because anyone wanted to go there, because that is where the exits lead. She has a separate reservation about the transactional interpretation which I want to plant now, because it is going to grow into something large later tonight. Her complaint is that it stays too close to specific experimental situations. She would like to see it move toward a more general picture in which the experimental setups, and crucially the observers, can be shown to arise from something more fundamental, rather than being handed to you at the start as furniture. As it stands, she says, it is overly focused on a setup where the instruments and the observers are already given. Hold on to that. The observers are already given. We will come back to it. Now, I am going to build the firewall, and I want to build it high, because this is the place where this material gets stolen. Nothing in any of this permits you to send a message backward in time. Nothing in any of this permits you to influence your own past. Nothing in any of this permits any version of the thing you have seen advertised online, where quantum physics is invoked to sell the idea that your intentions can reach back and rearrange what already happened. The reason is a theorem, and it is one of the most thoroughly tested results in the whole of physics. It is called no signaling. What it establishes is that in every one of these non-local arrangements, the statistics that any one party can observe on their own are completely unaffected by what the other party chooses to do. Alice can measure along any axis she likes. She can flip a coin to decide. Bob, staring at his own results, cannot tell the difference. The correlations only appear when the two sets of records are brought together and compared afterward. By somebody who has both, and getting both to the same place requires a phone call, an email, a courier, some ordinary signal moving at ordinary speeds through ordinary time. There is no channel, and in the all-at-once picture, the situation is even more final than that, because there is no traveller to load. You cannot put a message into a constraint. A constraint is not a vehicle. It is a rule about which whole patterns are allowed, and rules do not carry cargo. This is also why the two most abused experiments in modern physics are not what people say they are. The delayed choice experiment, proposed by John Wheeler in 1978 and carried out by Vincent Jacques and colleagues in 2007, is regularly described as changing the past. It does not. What it shows is that you cannot assume the past was already fixed in a particular way, independently of the eventual measurement. That is a statement about what you are entitled to assume. It is not permission to edit a record. The quantum eraser, proposed by Marlon Scully and Kai Druhl in 1982, and realized by Yoon Ho Kim and colleagues in 2000, has the same structure and gets the same treatment, and in that case the correlations only become visible when the two data sets are sorted against each other after the fact, which is not a very impressive time machine. I know that this can land as a disappointment. You're told there is a huge flaw in our understanding of time, you get an hour into it, and the presenter starts taking the time travel away. But I would like to try to reframe that because I think the disappointment is pointing the wrong direction. A message travelling backward through time is, when you actually examine it, a rather conservative idea. It keeps everything you already believe. It keeps causes and effects, senders and receivers, journeys and arrivals. It simply lets one of them run in reverse. It is the universe you already have, with a naughty exception. What is being proposed here is not that. What is being proposed is a universe in which two events across a stretch of time are locked together with nothing between them doing the locking, where the relation is real and the messenger does not exist and never existed and is not required. That is not a smaller idea than time travel. It is an enormously larger one, and it has consequences that reach well past physics laboratories into things you would never expect, including, as we are about to see, the meaning of the word because. But before we get there, we have to clear up a confusion that has been sitting quietly underneath this entire conversation. Because when physicists say the problem of time, they mean two completely different things, and depending on which one they mean, the answer runs in opposite directions. Part 7. Two different problems, both called time. Let us stop for a moment and put the pieces together, because we are about halfway through and the ground is about to move again. Here is where we are. We inherited a picture of physics in which the universe takes a state and grinds it forward, and that picture came from how we calculate rather than from anything we observed. There is an alternative in which the laws are constraints on whole histories, which permit patterns rather than producing moments. The evidence that first strained the old picture came from Bell's theorem and the experiments that confirmed it. And the reason those results feel spooky is that we insisted something must travel. Relativity then quietly converts any spatial non-locality into a temporal one, which means the strangeness cannot be contained where we put it. And when Adlam went looking, she found the assumption sitting inside a celebrated theorem, unexamined, doing work nobody had noticed. That is the case so far. Now for the part that trips almost everyone. When physicists talk about the problem of time, they mean one of two completely different things, and confusing them will wreck your understanding of both. The first is the arrow of time. This one you already know in your body. In the world as we live it, there are asymmetries everywhere. Glasses break and do not spontaneously reassemble. Coffee cools and never spontaneously reheats. Smoke leaves the chimney and does not come back. Your memory reaches backward and not forward. These asymmetries are so total that we scarcely register them as facts about physics at all. They feel like the furniture of existence. The problem is that the underlying equations do not have them. With one small exception I will get to, the fundamental laws of physics are time-symmetric. Run them backwards and they remain perfectly valid. Film a pair of billiard balls colliding and play the film in reverse, and nothing you see violates any law of mechanics. Film a cup falling off a table, and the reversed film is absurd, but not because any equation forbids it. So where does the asymmetry come from? The standard answer, going back to Ludwig Boltzmann in the 1870s, is that it is statistical. There are enormously more ways for a system to be disordered than ordered, so a system left alone drifts toward disorder simply as a matter of counting. Entropy increases because increase is what the odds overwhelmingly favour. That works beautifully going forward and collapses going backward, and here is why. The same counting argument, applied in reverse, says that yesterday should have been more disordered than today, which is false. Yesterday was more ordered, and the day before that, more ordered still, all the way down to a beginning that was in an extraordinarily improbable, extraordinarily low entropy condition. Adlam's summary of the difficulty is one I keep coming back to. You seem to have to impose the asymmetry, she says, by just deciding by fiat that the initial state of the universe was some special kind of state which can explain those asymmetries. And for many people that is not very satisfying. I would put it more bluntly, that is not an explanation. That is a place to keep the mystery where nobody will trip over it. Philosophers call the posited special beginning the past hypothesis, and its status remains unresolved. Is it a law of nature, or a brute fact about how things happen to be, or something else? Nobody knows. Roger Penrose has estimated the improbability of the required initial condition at 1 part in 10 to the power of 10 to the power of 123, a number so constructed that you cannot write it out in ordinary notation, only describe it. And note what that number is measuring. It is measuring how much of the arrow of time we have accounted for by assumption rather than by physics. The one exception to time symmetry is real, and I include it for honesty rather than because it rescues anything. The weak nuclear force does distinguish the directions. The Babar collaboration at the Stanford Linear Accelerator Center demonstrated direct time reversal violation in 2012 using entangled B mesons, and a related asymmetry has been reported in neutrino oscillations by a long baseline neutrino experiment in Japan. It is a genuine structural asymmetry in the laws themselves. It is also far too small and far too specialized to have anything to do with why your coffee cools, and no serious person claims otherwise. That is problem 1. Now problem 2, which is entirely different and considerably weirder. The problem of time in quantum gravity arises when you take general relativity and try to quantize it using a particular standard procedure, canonical quantization, in the jargon. You would expect to get a quantum theory of gravity out, possibly a difficult one. What you get instead is a surprise. Time evolution turns out to be what is called a gauge transformation. Let me unpack that, because the phrase does not carry its weight in ordinary language. A gauge transformation is a change of description that does not correspond to any physical difference. Measuring altitude from sea level or from the floor of your house are related by a change of description. The mountain does not care. So when the mathematics says that evolving the universe forward in time is a gauge transformation, it is saying something extremely specific and extremely strange. It is saying that the universe at one time and the universe at another are two descriptions of the same thing. Time evolution, in that formalism, is not physically real. The equation you arrive at is called the Wheeler-DeWitt equation, written in 1967, and its most famous feature is a piece of missing furniture. The time variable does not appear in it, not as a small quantity, not approximately, it is simply not there. The universe, on that formulation, does not evolve, it stands. Bryce DeWitt himself, by several accounts, was not fond of the thing and referred to it as that damned equation, which is the most human sentence in this entire video, and it leaves an obvious hole. If the fundamental description of the universe contains no time evolution, where do our experiences come from? Why does anything feel temporal? Why does it seem, so overwhelmingly, that we are doing things and obtaining outcomes? Adlam's position on the relationship between the two problems is careful. They are separate problems, she says, but she thinks it very likely they are linked. The story about why we have experiences that are temporal in nature must have something to do with thermodynamics and with the fact that we live in this strongly asymmetric regime. There is still work to be done to flesh out the connections, and she does not claim they are finished. But she does not think they are independent. There is a partial answer in the literature that I find quietly beautiful. In 1983, Don Page and William Wouters proposed that you can recover time from a timeless universal state by dividing the universe into two parts, a clock and everything else. Time then appears not as a thing the universe has, but as correlation between the two parts. From outside the whole system, nothing happens at all. From inside, tied to the clock, there is a sequence. In 2013, Ekaterina Mareva and colleagues built a small photonic version of exactly this and confirmed the behavior. Viewed from outside, the system is static. Viewed from inside, it ticks. And now I would like you to go back to the finished puzzle, because it has been waiting for us. Which cell came first? There is no answer, and we established that there is no answer. But suppose you put something inside the grid, something that can hold a record, that can retain a trace of some cells and not others, that has more of a mark of what lies on one side than on the other. That thing, sitting inside a pattern that has no first cell, would nonetheless experience an order. It would say, this came before that, and it would not be lying. It would be reporting accurately the structure of its own records. Which raises a question I have been circling all night and can no longer put off. If the universe does not evolve, and if the order we experience is a fact about record-keeping rather than about the pattern, then what happens to the word we use several hundred times a day without ever once inspecting it? What happens to because? Part 8. Causation was never down there. Emily Adlam's position on causation is the sharpest thing in her entire body of work, and it is the one I would ask you to carry out of tonight if you carry nothing else. She does not think there is any causation in fundamental physics, not hidden causation, not causation we have failed to identify, not a quantum generalization of causation waiting to be formalized, none. She thinks the concept simply does not apply at that level, and that a great deal of very serious research has been spent trying to install it in a place it does not fit. Her reasons are 3, and they are worth taking one at a time, because each one is the sort of observation that seems trivial until you notice what it costs. First, causation clearly has something to do with thermodynamics. It is bound up with the entropic arrow, with the direction in which order dissolves. Causes come before effects, and before is a thermodynamic notion. We have just spent a part establishing that the fundamental equations do not supply it, and that the arrow has to be imported from a special initial condition. Second, causation is clearly related to perspective, specifically to the perspective of macroscopic observers like us, and to what we can and cannot achieve. The causal structure we perceive tracks the joints in the world that creatures of our size, with our timescales and our resolution, are able to lean on. Third, causation is bound up with intervention. When we say one thing causes another, we are very often telling a story about what an agent could accomplish by intervening on a variable. Flip this switch and the lamp comes on, and it is the flipping that carries the causal weight. Take away the possibility of intervening and the causal claim thins out into a mere correlation. Now look at those 3 together: thermodynamics, perspective, intervention. Every one of them is macroscopic. Every one of them is a fact about large, warm, slow, embedded things with limited information and the ability to push on the world. And so, Adlam argues, it is incorrect to think of causation as something that inheres in the microscopic world at all. I want to be careful about what this does and does not say, because it is easy to hear it as a claim that the fundamental world is structureless, and that is not the claim. She thinks there are certainly important kinds of structure in the microscopic world that we need to think about. Her point is that those structures are not causal in the ordinary sense, and so it is not going to be particularly helpful to model them in causal terms. What is down there instead? Her answer is a word borrowed from philosophy, and it is worth learning because it is doing precise work. Modal structure. Modal is the word philosophers use for facts about what is possible and impossible, not what happens, what could happen, and what could not. And the most familiar example of modal structure, the one everybody already knows without the label, is causal structure. Causal structure tells you that certain things can bring about certain other things and cannot bring about others. It is a map of possibility with a direction stamped on it. But if causation is not fundamental, then causal structure cannot be the most general kind of modal structure. There has to be something underneath it, something that does the same job of sorting possible from impossible, without the direction, without the pushing, without the agent leaning on a lever. Adlam thinks the world has some other kind of structure, similar in character to causal structure but more general than it, and that, she says, is where she would expect the all-at-once constraints to live. This is where her view differs, gently, from her nearest colleagues. Eddie Kemming Chen and Sheldon Goldstein are inclined to treat these all-at-once constraints as a fundamental primitive, the bedrock, not further analysable. Adlam prefers to think of them as a form of modal structure, in keeping with a broadly structural approach to physics in which what is real is the pattern of relations rather than the thing standing in them. She describes the two positions as not necessarily incompatible, more a difference of emphasis. I mention it because it is the sound of a small field arguing about foundations in good faith, which is a nicer sound than physics usually makes in public. There is a rival position she is arguing against, and naming it makes her own view sharper. It is called human supervenience, after the philosopher David Hume, and it holds that the world is just a distribution of categorical properties over space-time. One thing, and then another thing, and then another thing. No deeper structural connections at all. On that view, everything else, laws, causation, necessity, has to somehow depend on that bare distribution of facts. And so the human says that the laws of nature do not make things be the way they are. The laws are just convenient descriptions of the way things happen to be, the best available summary of whatever actually occurred. Adlam's constraints are meant to be more than a summary. They are meant to be real modal structure, doing genuine work, telling you which whole histories are permitted and which are not. That is the difference between a law that governs and a law that merely reports, and it is one of the oldest arguments in the philosophy of science. So what does her picture actually contain at the bottom? She lays it out in 3 steps. You start with a space of possible courses of history, every complete pattern the world could have been, which might be thought of as an ensemble of those human distributions of facts across space-time. Then you have constraints, which determine which elements of that set are allowed by the laws. Then some element of the allowed set is selected and made actual. Possibilities, narrowed, one made real. She is honest that this is unfinished, and the honesty is worth repeating because it is rare. In her earlier work, she simply took space-time as given and had the constraints govern how things are distributed across it. She says plainly that this cannot be the right final answer, because modern physics, and quantum gravity in particular, suggest that space-time itself probably emerges from something more fundamental. How to formulate that properly is not clear, partly because quantum gravity is not itself formulated. There are a great many open questions there, and she does not pretend otherwise. But set the unfinished business aside for a moment, because I want to stay with the central claim, and I want us to feel it rather than file it. If causation is macroscopic, if it belongs to thermodynamics and perspective and intervention, to creatures of a certain size who can push on things, then the word belongs to you, not to the universe, to you. Every explanation you have ever accepted has that word in it somewhere. The bridge fell because the bolt sheared. She left because she was tired. I am the way I am because of what happened when I was 9. Every plan you have made runs on it. I will do this, because then that. Every regret you carry is built out of it, and regret is possibly the purest causal reasoning a human being ever performs. A complete counterfactual model of a world in which you did the other thing. And the claim on the table tonight is not that any of those sentences are false. They are true. They are true in the only register where causal truth is available. The claim is that they are true at your scale, about your scale, and that the world underneath is not organized around them at all. Underneath, there is no because. There is a pattern and a rule that permits it, and no arrow anywhere. That is not nothing to be told. Take a moment with it. I did. There is an image that comes up in Adlam's conversations that I have found genuinely helpful, and I want to introduce it now because we will need it again before the night is over. Picture a bird crossing the sky. You take a photograph. From the photograph you extract a position and a velocity. It is here, and it is moving that way at that speed. And from those two numbers you can compute where the bird will be in 10 seconds. Good. Standard physics. Now notice what you called those two numbers. You called them the initial conditions. Why initial? You could have taken the photograph 10 seconds later and run the calculation backward. You would have got the same curve. The bird's whole path lies in the air from where it left the branch to where it lands, and every point on that curve determines every other point. Nothing about the mathematics identifies one end as the start. You called it initial because you happened to be standing there when you pressed the button. Adlam's response when this analogy is put to her is that it is a great analogy, and that she would say much the same about time evolution. There is no particular reason to privilege one point, and certainly the physics does not tell you that you have to. Hold on to the bird. We're going to need it later, when the question stops being about birds, because there is something I have skated past 3 times now, and it is time to stop skating. Causation is macroscopic, which means it belongs to observers. The arrow of time shows up where records are kept, which means it belongs to observers. Every road tonight arrives at the same place. So what precisely in physical terms is an observer? Nobody can tell you. And Adlam thinks that this, not string theory, not dark matter, not the origin of the universe, is the largest unsolved problem in physics. Part 9. The person doing the physics. When Adlam is asked to name the largest unsolved problem in physics that interests her, she gives an answer she herself describes as not very original, and then immediately makes it original by explaining why. The measurement problem, she says, and not primarily because it is intellectually interesting, though it is, but because it seems to her closely linked to a variety of concrete problems people are working on in modern physics right now. Her specific claim is this: in the work on quantum gravity, a lot of the issues the field is genuinely struggling with are ultimately to do with the nature of observers and the nature of observation. Solving the problem of time, she says, is all about trying to understand how to put the observers and their theories together in a way that reproduces the kinds of observations we expect to see. And that makes her think there is an issue here where we never really came to grips with how to think about observers in the context of ordinary quantum mechanics, and that this failure, a century old and never repaired, is what is holding us back from making progress on everything downstream. That is an unusually specific diagnosis, and I want you to notice what it accuses. It says the reason we cannot quantize gravity might not be that gravity is unusually difficult. It might be that we have been carrying a broken part since 1927, and it only fails under load. So the obvious follow-up is the one anyone would ask. What is an observer? Is it the same as a measuring device? What counts as a measurement? Her answer is 4 words long, and it is the most honest sentence in the material. That is exactly the problem. We do not know how to define observers in concrete physical terms. We have an intuitive notion of what an observer is, a person with an instrument roughly, or an instrument on its own if you're feeling generous, and we know what we expect observers to see. But it remains very unclear how to properly model an observer within quantum mechanics, and every interpretation of quantum mechanics says something different about how observers should be represented, which means the disagreement is not a footnote, it propagates. The choice you make about observers in ordinary quantum theory determines what you can even say about observers when you try to build quantum gravity on top of it. Now here is where her position becomes genuinely unusual, because she wants to change what kind of problem the measurement problem is. It is nearly always framed as an ontological problem. We need to know what is really there. We need to know what is really happening when a measurement occurs. Does something collapse? Does the world split? Was there a particle all along? Those are questions about furniture. What exists? Adlam thinks the deeper importance is epistemic. The measurement problem matters, she argues, precisely because it ties to a question about how we could possibly know the things we are supposed to know. How do we make sense of the empirical confirmation that quantum mechanics has received? Any interpretation of quantum mechanics must tell a consistent story about how we could have come to know about the theory in the first place. If it cannot, then whatever else it is not a picture we are entitled to believe on the evidence. because it cannot explain how the evidence reached us. She has said that she is on something of a crusade about this, and that she would like the field to spend far more attention on the epistemology of the measurement problem than it does. Her reasoning is that this requirement, make the epistemology coherent and consistent within itself, is a good way of narrowing down the possibilities and understanding what a viable solution actually looks like, and she has a specific target. The many worlds interpretation, she thinks, has a real problem here. The difficulty runs like this. Many worlds has a long-standing difficulty giving meaning to assignments of probability to measurement outcomes, since on that picture every outcome occurs in some branch. That difficulty is well known, and there is a substantial literature attempting to solve it. But notice the specific form of the trouble Adlam is pointing at. In the many worlds context, it is hard to justify the claim that you should expect to see high probability outcomes. And if you cannot expect to see high probability outcomes, then you cannot use the outcomes you have actually observed as evidence for the theory, because you have no idea whether what you saw was something the theory assigned a high probability or a low one. The observation cannot be connected back to the structure of the theory you were trying to learn about. The circuit is broken. Data comes in and cannot reach the theory. That is not a knockdown argument, and the theory's defenders have responses. But it is a different sort of objection from the ones many worlds usually faces, and it is aimed at a joint most people never look at. So what does she prefer? Her instinct is relational. Relational quantum mechanics is Carlo Rovelli's interpretation, developed from 1996 onward, and its core move is to say that quantum states are not absolute. They are defined relative to observers, and on that view, any physical system can count as an observer. There is nothing special about people or laboratories or things with minds. What draws her to this is a lesson she takes from both general relativity and quantum gravity. Making sense of observers, she thinks, is probably going to require understanding them in relational terms, understanding observations as things that happen relative to observers, rather than as facts sitting out there in the world by themselves. She thinks that insight is relevant for ordinary quantum mechanics too, and she is clear that it is an ongoing project to make it work coherently, because there is a problem with it, and she has been one of the sharpest people identifying it. If you're really serious about observer centricity, if you follow it all the way down, you arrive at a picture in which every observer has their own little reality, and they are not able to communicate with each other about it in any absolute sense. Everything is true relative to somebody. Nothing is true full stop, and her objection to that is not that it is unpleasant, it is that it is incompatible with the practice of science. Science is a social activity. That is not a sentimental observation, it is the load-bearing one. The objectivity of science rests on the fact that many different people make observations and then share them, and check one another, and disagree, and converge. Take away the possibility of two observers genuinely comparing what they found. Not each in their own private reality, but actually comparing, and you have removed the mechanism by which any of this was ever established, including, incidentally, quantum mechanics itself. She finds views of that kind incoherent, and she says so about the strongly observer-centric interpretations without softening it. So she and Rovelli tried to fix his own theory. Their joint paper proposes an extra postulate, which they call cross-perspective links. The requirement is that all the information possessed by an observer must be stored in physical variables of that observer, and therefore be accessible by measurement to other observers. Concretely, if Alice measures some variable, and nothing subsequently happens to Alice that destroys the record stored in her physical variables, then when Bob later measures the physical variable that represents Alice's information about that measurement, Bob's result will match Alice's, which is, when you say it in plain language, a formal guarantee that two people can agree about what happened. The fact that this needed to be added as a postulate, rather than falling out of the theory, tells you how strange the foundations of quantum mechanics really are, and they still disagree about whether it was necessary. Rovelli is not convinced. He thinks it may be enough that it is relationally true, within his own perspective, that he seems to have access to yours, that agreement inside a perspective might be all the agreement there is or needs to be. Adlam thinks that does not solve the epistemic worries about the role of social inquiry in science, and that an absolute story is required. The argument is live. Other researchers have published criticisms of the modified scheme itself, arguing it introduces problems of its own. This is contested, working science, being argued out in journals right now, and I would be misleading you if I presented it as settled. Her verdicts on the other interpretations are worth having, because they show a person marking her own confidence honestly. The strongly observer-centric views she finds incoherent, for the reason above. The primitive ontology approaches, meaning the pilot wave theory and the spontaneous collapse models, she treats far more gently. She would not say they fail. What she says is that at present we do not know how to reproduce the whole of quantum field theory within them, and there are reasons to think that may be very difficult or never possible. Never say never, she adds. But until it can be shown to work, that is a compelling reason to worry. And her current research is a small technical problem that sits directly on top of the largest question in this video. Kaslev-Bruckner raised an objection to relational quantum mechanics. It does not seem to make sense to call a single qubit an observer, because there is no way to get a well-defined basis in which a qubit could make an observation, so no well-defined value could come out. Adlam thinks he is right. Her resolution is that the description of the world relative to a qubit is not going to be a full quantum description at all. A qubit simply does not have the physical resources to define something that rich. So she is working out what the world does look like from the standpoint of something that small, and therefore what range of observations a thing that simple could possibly make. Which is, if you step back far enough, a person trying to find the smallest possible thing that can be said to notice something. And that is such a strange and lonely question to be working on that I want to leave it there for a moment and take you somewhere else entirely, to a completely different corner of physics, with nothing to do with time, where the very same flaw turns out to be waiting. Part 10. The same flaw, in a different room. I want to leave time alone for a while and take you to a completely different part of physics, because something happens there that I think is the strongest evidence that we are looking at a habit of mind rather than a local difficulty. The corner in question is called renormalization, and it sounds forbidding, but the idea underneath it is one you already understand. Physics looks different at different scales. Water, described at the scale of your kitchen, has a density and a viscosity and a boiling point. Described at the scale of molecules, it has none of those things. It has hydrogen bonds and collision rates. Both descriptions are correct. Neither is the other, and when you want to move between them, you need a set of tools that tells you how the quantities in one description translate into the quantities in the other. In quantum field theory, that set of tools is renormalization, the machinery for moving between energy scales, or equivalently between length scales, and for working out how the numbers change as you go. Now, there is a problem in quantum field theory that has bothered people for a long time, and it is a fine-tuning problem. In certain cases, it turns out that the values of two distinct fundamental constants have to be adjusted against each other with extraordinary precision in order to produce the observed value of a constant at a higher scale. The most famous version of this is called the hierarchy problem, and it concerns the enormous gap between the scale at which the weak nuclear force operates and the scale at which gravity would become strong. To get the world we see, quantities down at the bottom appear to have been set against each other to an accuracy that looks like a conspiracy. Physicists hate this, not because it is impossible, the numbers are what they are, but because a coincidence that precise feels like a message you have failed to read. It helps to have a picture of what that kind of precision means. Imagine two enormous numbers, each with dozens of digits, arrived at by completely independent roots, and imagine that when you subtract one from the other, the answer is small, not zero, small, and exactly as small as it needs to be for atoms to exist and for you to be sitting there listening to this. If you found two such numbers written on separate pieces of paper in separate rooms, you would not conclude that you had got lucky. You would conclude that somebody, somewhere, had copied one from the other. The whole discomfort of fine-tuning is the sense of a copy having been made and the original having gone missing. Adlam's observation, in an exploratory paper on whether reductionism is false, is delightfully simple. What if you have the direction of explanation backwards? Suppose the higher level constant is the fundamental one, and the smaller scale constants are in fact derived from it. Then the fine-tuning evaporates instantly. The two small scale quantities match each other so precisely because they are both fixed by the actual value of the higher level constant. There is no conspiracy. There is a shared cause sitting above rather than below. The immediate objection is the one any physicist would raise, and it is a good one. Coarse graining is many to one. There are enormously many microscopic arrangements of water molecules corresponding to a single macroscopic temperature, which is why you cannot read the molecules off the thermometer. Information is lost going up, so the large scale cannot possibly determine the small. Her reply is technical and rather beautiful. That objection is correct for ordinary coarse graining. But renormalization transformations are not ordinary coarse graining. In the underlying mathematics, they are one-to-one. Many of the approximations physicists actually use to do renormalization in practice are not invertible, but there are good reasons to think that the real underlying transformations are. And if they are, then away from certain special points you can go from small scales to large scales, or from large scales to small, and it is the same thing from the point of view of the mathematics. There is no obvious sense in which the physics is telling you that the small things must explain the big things and not the other way around. The difference between the two cases is worth making concrete, because everything hangs on it. Take a deck of cards and record only how many are red. That is many to one, catastrophically so. An enormous number of distinct orderings give the same count, and from the count you can never recover the deck. Now take the same deck and cut it precisely in half, then put it back. That is 1-to-1. Nothing was lost, and given the result you can work backward to exactly what you started with. Adlam's claim is that the honest mathematics of moving between scales in a field theory is much more like the second operation than the first, even though the approximations we use in practice throw information away and therefore feel like the first. The special points are called fixed points, and they do complicate matters because at a fixed point many solutions genuinely do map to one. But fixed points occur at very small scales and at larger scales alike. So invoking them does not particularly favour one direction of explanation over the other, since they turn up at both levels. There is a precise way to say all of this, and it was put to her in an exchange I enjoyed. The renormalization group, despite the name, is not really a group in the algebraic sense, because not every element is invertible. It is closer to what mathematicians call a monoid. But most of the elements are invertible, and where they are, no scale is privileged, in the same way that an affine space has no privileged origin. You can measure from anywhere. Adlam's response was simply, "That is right." I should be careful to give this the label she gives it. She is not committed to the view that reductionism is false. The paper is exploratory. She is interested in whether inverting the direction might be one way to resolve some of the problems quantum field theory encounters, and she says so in exactly those terms. Effective field theory, the mainstream framework, reads the hierarchy of scales bottom up as a matter of course, and the overwhelming majority of working physicists have no intention of stopping. This is a minority thought, offered as a possibility. But look at the shape of it. In the case of time, we assumed there was a privileged moment, the beginning, and a privileged direction of production, from earlier to later. Then someone looked at the mathematics and found that the mathematics does not supply either one. The bird's trajectory has no initial end. You called it initial because of where you were standing. In the case of scale, we assumed there was a privileged level, the small, and a privileged direction of explanation, from bottom to top. Then someone looked at the mathematics and found that the mathematics does not supply that either. Away from fixed points, the transformations run both ways and neither end announces itself as fundamental. Two different fields, two different sets of equations, the same missing arrow, imported by us in both cases, and then treated as a discovery about the world. That is what convinces me this is worth 2 hours of a Saturday night. If the only claim were about time, you could file it as a curiosity about a hard subject. But when the identical error turns up in a completely unrelated area, argued by the same person on entirely different mathematical grounds, you are no longer looking at a puzzle. You are looking at something about how minds like ours build explanations, the tendency to reach for a starting point, to ask what came first and what is made of what, and to assume that the answer must exist because the question is easy to form. We are creatures who solve puzzles by starting somewhere. It is not surprising that we built a physics that starts somewhere. What is surprising is how long it took anyone to check. And now I want to take this in a direction you will not see coming, because the constraint picture does one more thing, and it is the sharpest thing it does. It changes what a probability is, which sounds like a technicality. It is not a technicality. It turns out to be a knife pointed at one of the largest and most beloved ideas in modern physics, an idea you have almost certainly absorbed as more or less established, that appears in films and novels and late-night conversations, and that a great many extremely serious physicists believe. And the argument that undoes it starts, of all places, with a woman waking up in a plain room, not knowing what day it is. Part 11. Which one of you is you? Before we get to the woman in the room, We need to talk about probability, because probability turns out to be in worse shape than almost anybody outside philosophy realizes. Ask a physicist what a probability is, and you will usually get one of three answers, and Adlam is not fully satisfied with any of them. The first is frequentism. A probability is a long-run relative frequency. The chance of heads is 1/2, because in a very long series of flips, about half come up heads. This is useful, and it is what most working scientists mean in practice, but it has serious difficulties around the edges. What is the probability of a single event that will only ever happen once? What is the reference class? This coin, all coins flipped by tired people at midnight. And what happens when the series is infinite, where the mathematics starts producing answers that depend on how you order things? The second is subjective Bayesianism. A probability is a degree of belief, and the rules of probability are rules for keeping your beliefs coherent. This is elegant and enormously productive, and Adlam's objection is that it does not do justice to the fact that certain probabilities really do seem to be out there in the world rather than merely in our heads. The half-life of a radioactive isotope does not feel like an opinion. The third is dispositionalism. A probability is a propensity, a tendency a system has to produce an outcome. Her assessment is that these accounts are quite mysterious in themselves, and, this is the point that matters for tonight, very hard to reconcile with all-at-once physics. A propensity is a forward-looking notion by construction. It is a thing the present has, aimed at the future. Remove the forward-looking machinery, and it is not clear what a propensity would even be. What she considers most promising is an approach called nomic frequentism, proposed by the philosopher John Roberts, in which probabilities are understood in terms of laws that require the frequencies to look a certain way. And inside the constraint picture, this becomes not merely one option among several, but the natural one. Here is why. If laws are global constraints applying to the whole of history, then a probabilistic law is simply a constraint of a particular shape. It says something like, the relative frequency of this outcome, across all instances of this type of measurement, across the entirety of history, must have this value, or must fall within this range. That is a perfectly ordinary constraint. It is just a constraint on a tally instead of on a configuration. And notice what that does. It is similar in spirit to frequentism, but it dodges frequentism's worst problem, because it is not merely saying that probabilities are whatever the frequencies happen to turn out to be. It really is saying that the laws constrain the frequencies and require them to have certain values. The law is doing work rather than describing an accident. Eddie Chen and Jeffrey Barrett have both been developing this direction, and Adlam regards it as the most promising thing available. I want to give you the reframe in the most vivid form I can, because I found it genuinely disorienting the first time it landed. In this picture, the law does not assign a chance to your coin flip. Your coin flip does not have a propensity. Nothing hovers over the coin weighing the options. What the law does is tell the universe what the ledger has to look like when every coin flip in the entire history of the universe is added up. The odds are not in the coin, the odds are a condition on the whole book, right? Now the woman in the room. You're lying in a plain bed in a plain room, and you have just woken up. There is no clock, there are no windows, there is nothing on the walls. The room has been made deliberately featureless, and that is the point of the room. You know exactly what has been done to you, because you agreed to it. You were put to sleep. A fair coin was flipped. If it came up heads, you're being woken once today, and that is the whole experiment. If it came up tails, you're being woken twice, today and tomorrow. And between the two wakings, your memory of the first one is erased, so that both wakings are subjectively identical in every respect. So you sit on the edge of the bed in a room designed to tell you nothing, and you try to work out where you are in your own life. Is this the only waking? Is it the first of two? Is it the second of two with a whole erased day behind you that you will never recover? Nothing in the room can help you. Your own memory cannot help you. That is precisely the thing that was taken. You are a person who cannot locate herself in her own experiment. And someone asks you, gently, what odds you would now give on the coin having come up heads. This is the Sleeping Beauty problem, introduced to the philosophical literature by Adam Elgar in the year 2000, and it has generated hundreds of papers about a puzzle you can state in 4 sentences. The majority position, and Elgar's own, is that on waking you should shift your credence in heads down to 1/3, because a tails world contains twice as many wakings as a heads world, and you are more likely to find yourself in a world with more of you in it. Adlam disagrees, and her disagreement runs through a distinction she thinks the whole literature has been missing. There are two kinds of not knowing where you are. The first she calls pure self-locating uncertainty. This is when you do not know which of several locations you occupy, and all of those locations exist within one and the same world. The standard illustration is another case of Elgar's, from 2004, involving a man who believes himself to be Dr. Evil and receives a credible message informing him that a subjectively identical duplicate of Dr. Evil has been created and placed somewhere. He now does not know whether he is the original or the copy. But both of those people exist. They are both in the world right now, both wondering. The second she calls superficially self-locating uncertainty. This is when you do not know where you are, but the candidate locations belong to different possible worlds. Suppose you wake and have not looked at a clock, so you do not know the time. That is uncertainty about your position in time, but in every possible world there is exactly one time at which you actually woke. The different possible times you could be waking at belong to different possible worlds, each corresponding to a different way things could have gone. That distinction sounds like bookkeeping, and it is not. Because Adlam's claim is that for superficial self-location, there is a right way to assign your credences. You inherit them from your scientific theory, which tells you how likely each of those different possible worlds is. Whereas for pure self-location, there is nothing whatsoever that could compel or constrain you to assign credences in any particular way. Any assignment is permissible. There is no fact about how likely it is that you are the original rather than the copy, because both are actual, and probability was never designed to answer that question. Apply that to the room. The coin flip is a superficial matter. Heads world and tails world are different possible worlds, and your theory says each has probability 1/2. Which waking you are currently in is a pure matter, since in the tails world both wakings actually happen. The correct procedure, she argues, is to assign the superficial credences first, from the theory, and then arrange your pure credences however you like. And because the pure information cannot reach back and alter the superficial assignment, learning what day it is changes nothing. The probability of heads is 1/2, before and after, always. Hers is what the literature calls the double halfer position. Now here is why any of this belongs in a video about time, and it is the sharpest turn of the night. Both of the great multiverse pictures in modern physics need pure self-locating credences in order to work. The cosmological multiverse, with its endless pocket universes, and the many worlds interpretation of quantum mechanics, with its branching, both face the same demand. To extract any prediction at all, you must assign probabilities to which universe or which branch you are in. And in both cases, those other universes and branches are actual, which makes the required credences pure in exactly her sense. So those approaches are predicated on the assumption that there is some objectively right, uniquely correct way to assign pure self-locating credences. There is a right answer and a wrong answer to the question of how likely it is that you are this copy rather than that one. And if she is correct that no such constraint exists, then you cannot get meaningful predictions out of theories of that kind. And if you cannot get predictions out, you cannot get evidence in, because there is nothing to predict and then check. The theory becomes untestable, not for practical reasons, but structurally. She has not, she says, discussed this with Sean Carroll, who is among the most prominent defenders of the many worlds picture, and who holds that certain constraints on self-locating credences can supply the probabilities. Her view is that there are no rational constraints on self-locating credences in that setting, and so any model that takes them as a starting point cannot be right. I want to flag clearly that this is a philosophical argument and a contested one. There are sophisticated attempts by David Wallace and Simon Saunders and others to derive the probabilities in many worlds from decision theory, and her objection sits upstream of those derivations rather than refuting them line by line. Nobody has settled this. But it is a real argument, published, aimed at the foundations of an idea that most people have absorbed as more or less established, and it comes from a picture of law that started with a Sudoku grid. Which brings us finally to the part you have been quietly worrying about since the first 10 minutes. If the whole of history is selected at once, if there is no producing, no working out, no next moment being manufactured out of this one, then what exactly are you doing right now? Part 12. What this does to you. Let me say the frightening version out loud, because you have been carrying it for an hour and it is only fair. If the laws of nature select the whole of history at once, if there is no producing, no grinding forward, no moment being manufactured out of the last one, then the moment you're about to have has, in some sense, already been selected. Not caused, not predicted. Selected, as part of a pattern that includes everything you will ever do. And if that is right, then the sense that you are deciding right now, in this pause between one sentence and the next, is the strangest kind of illusion. Not a false perception of the world, but a false perception of what you are. That is the fear. Now let me take it apart, carefully, because I think it is wrong, and more importantly, because Adlam thinks it is wrong, and she is the one who built the picture. She is straightforward about what this does cost you. Some people, she notes, have thought that what matters for free will is the idea that the future is genuinely open, that in this moment, as I am acting, there is no fact of the matter about what my action is going to be. In an all-at-once model, that particular way of thinking about free will is not available to you. The whole of the universe exists at once. I am acting now, but from the atemporal standpoint there is already a fact about what my action is going to be. That much is gone. She does not soften it. But she does not conclude that free will is therefore an illusion. Her conclusion is that we're going to have to be more careful about how we analyze free will and what we mean by it, which is a very different thing from a surrender and a much more useful one. There is one detail here that almost everybody gets wrong, and I want to plant it firmly because it removes the escape hatch most people reach for. This has nothing to do with determinism. People assume that if the world were fundamentally random rather than deterministic, freedom would be rescued, that indeterminacy at the bottom leaves room for you at the top. It does not, and in the all-at-once picture the reason is unusually clear. Even a probabilistic model in this framework looks like one of two things. Either it is a frequency constraint of the kind Eddie Chen has proposed, requiring the tally of outcomes across all of history to come out a certain way, or the course of history is selected in a probabilistic manner from some set of possibilities. Either way, you end up saying that the course of history is determined all at once. There is no sense in which I am acting now, and my future actions are still open. From the atemporal point of view, they have already been chosen. Randomness does not save you. It never did. A coin flip inside your head is not a decision. It is weather. So we need something better than randomness. And here it is, and it is the reason I wanted to spend tonight on this. Go back to the bird. There is a bird crossing the sky above you. Watch it. It leaves a branch somewhere behind you, and it will land on a wire somewhere ahead, and between those 2 points there is a curve, a single continuous path through the air, every point of it as real as every other. Now take the whole curve at once. Do not follow the bird along it. Hold the entire arc in your mind from branch to wire, the way you would hold a drawn line on a page. It is all there. Nothing on it is waiting to happen. Find the beginning of that line. You cannot, in any sense the mathematics respects. You could compute forward from the branch. You could compute backward from the wire. Every point on that arc fixes every other point, and no point wears a label. You call one end initial because you happened to be standing there when you looked up. And now the thing I want you to sit with. The line does not push the bird. The line is not a rail. It is not a groove cut into the afternoon that the bird is sliding helplessly along. It is not an instruction, and it is not a cage. The line is the bird's flying. It is what flying looks like when you take the whole of it at once instead of a slice at a time. There is nothing on that curve forcing anything, because the curve is not a separate thing from the flying that could do any forcing. That is the argument, and it is not a comforting metaphor pasted over a bleak physics. It is precisely the physics. Laws in this picture do not push. We established that in the second part of tonight, with a puzzle. Some rules push, and some rules permit, and constraint laws are the permitting kind. They sort whole patterns into allowed and not allowed. A rule that permits cannot force you, for the same reason a grammar cannot write your letters for you. And here Adlam's view of causation, the one that seemed so cold an hour ago, quietly turns into the warmest thing in the video. Her position is that understanding how the history comes about is not going to involve any kind of causal story. It will be some more general modal constraint that selects the history. Causation appears at a much higher level of description, and is probably only relevant in the kinds of regimes where you have agents taking actions. And therefore, she says, it is perfectly possible to say that in some fundamental sense the history was already there, and was selected all at once, and nonetheless the agent is the cause of their action, because causation is only suitable in that regime of description anyway. Insofar as there is such a thing as causation at all, it remains true that the agent is causing their actions. Read that again if it went past quickly, because it is the reversal the whole night has been building toward. You were afraid that the universe was causing you. It is not, because the universe does not do causing. That is not a thing the fundamental level contains. Causation exists exactly and only at the scale of thermodynamics and perspective and intervention, the scale of large, warm, embedded creatures who can lean on the world and change it. Which is to say, your scale. Your choices are not a lesser kind of causation, borrowed from a real kind further down. They are the real kind. There is no competitor beneath them. The fatalism people fear is the pushing picture wearing a grim face. It says the past forces the future, and you are downstream of a shove that happened before you were born. This picture denies that anything forces anything. It is not fatalism with worse manners. It is the removal of the very thing fatalism was made of. One last piece of the furniture, and then we can go home. There is an old argument in philosophy between presentism and eternalism. Presentism holds that only the present moment is real, that the past has gone and the future has not arrived, and that reality is a thin, bright edge moving forward. Eternalism holds that the whole of history is real at once, with no privileged present, and that now is like here, a word that means wherever the speaker is standing. Adlam is, as you would expect on the eternalist side. Her reason is not a preference. It is that presentism is very hard to make compatible with relativity, because relativity denies that there is any global present at all. If different observers, moving differently, disagree about which distant events are happening now, and we watch that happen in this very video, on a ship passing 2 rooms, then it is unclear what the present even is on the presentist picture. People have tried to reformulate presentism in relativistic terms, and she finds all of those attempts a bit ad hoc and not very compelling. Which means the whole of history being real is not the exotic option here. It is the conservative one. It has been the mainstream implication of Einstein's work for over a century, and most people have simply never been told. I want to be careful about one word before we finish, because it does more damage than any other in this subject. Emergent does not mean unreal. If it turns out that the flow of time is something that appears at the level of records and thermodynamics, rather than something written into the fundamental laws, that does not make your Tuesday a hallucination. Temperature is not a property a single molecule has. Temperature emerges from the statistics of enormous numbers of them, and yet your hand knows perfectly well the difference between a hot cup and a cold one, and no physicist has ever suggested otherwise. So, we have taken the whole thing apart. We have found the assumption, traced where it came from, watched it hide inside a theorem, watched it decide the meaning of an experiment, watched it reappear in a corner of physics with nothing to do with time, and watched what it does to probability and to the multiverse and to you. Which leaves one thing left to do tonight, and it is the thing the title promised. Name the flaw. Plainly, in one sentence, with no hedging. And then tell you, honestly, exactly how frightened you ought to be. Part 13, The Flaw, Named Plainly. Here it is, in one sentence, with nothing hedged. The huge flaw in our understanding of time is that we mistook the method for the world. Time evolution is how we solve problems. It is what a mind with a pencil does when it wants to get from something known to something unknown, one step at a time, because one step at a time is the only way a mind with a pencil can move. We built that technique 3 centuries ago. It worked so extravagantly well that it built bridges and put people on the moon, and predicted particles before anyone had seen them. And somewhere along the way we stopped noticing that it was a technique, and started treating it as a description of what the universe is doing when nobody is calculating. The universe, on this reading, is not doing that. The universe is not doing anything. There is a pattern, and there are constraints that permit it, and we are inside it, keeping records, and the keeping of records is where before and after come from. Some rules push, some rules permit. When I gave you that phrase, hours ago, it was a distinction about equations, and it sounded like housekeeping. Here is what it means now. You have spent your life inside a story in which you are being pushed, by your childhood, by your circumstances, by the initial conditions of a universe you did not choose, all of it grinding forward and producing you as an output. That story is the pushing picture, and it is not obviously what physics says. The alternative is that you are one of the things a pattern permits, not manufactured, not forced, allowed. Now the honesty, because you have given me your evening and you have earned it. This is a minority position. It is formally published in Foundations of Physics and Entropy and the Proceedings of the Royal Society. It is argued by credentialed people with doctorates in physics. It is taken seriously enough in quantum foundations that conferences are held about it and rival camps argue about vocabulary. And it is not the consensus view of physics, it has not been demonstrated, and no experiment has yet been performed that decides between it and the ordinary picture. Anyone who tells you otherwise is selling something. Adlam herself is the most careful person about this, which is why I trust her. She does not claim to have solved the measurement problem, and says plainly that adopting an all-at-once model does not by itself solve it, because the measurement problem is largely about how to model observers, and telling an all-at-once story does not answer that. She does not claim to have derived space-time. She took it as given, and says that cannot be the right final answer. She thinks consistency conditions might give you something like a time dimension, and something like the light cone structure, and she says outright that she does not know how to get 3 spatial dimensions out of them, and that it would be great if there were a way. There is a way this could eventually be tested, and it is worth naming because it keeps this from being pure philosophy. If constraint-based laws are real, they might one day explain relationships between quantities we currently treat as independent, correlations between seemingly unrelated physical constants, values that turn out to be locked to each other for a reason. Adlam has said that finding such correlations would be a compelling piece of evidence that this way of thinking is right. That is a distant handle, but it is a handle, and it is the kind of thing that ends arguments, and now the shape of the whole thing, which I have been circling all night and can finally say. Every road to what time is arrives at the observer, the arrow of time shows up where records are kept. Causation lives at the scale of creatures who can intervene. The rate of time depends on who is measuring. Even the order of 2 distant events depends on who is asking, and every road to what an observer is arrives at physics we do not have. Nobody can define an observer in concrete physical terms. Every interpretation of quantum mechanics answers differently. The most serious current work is a person trying to work out what the world looks like from the standpoint of a single qubit. So the circle does not close, and the reason it does not close is that the thing asking the question is a physical system made of time, sitting inside the pattern, trying to ask about the pattern from a chair that is one of the filled squares. You're not outside the puzzle looking in. You're one of the cells asking about the grid. So how frightened should you be? Let me answer that properly because the title made a promise. You should not be frightened that time is an illusion, because nothing here says that. Adlam holds that the whole of history is real. Emergent is not the same as unreal, and your Tuesday is not a hallucination. You should not be frightened that nothing you do matters, because the line does not push the bird. Causation is a large-scale phenomenon, and you are large. Your choices are not a diminished imitation of some realer forcing underneath. There is nothing underneath. They are the only causing there is. What you should find unsettling is smaller than either of those and much bigger. We do not know what we are. Physics cannot yet say in physical terms what an observer is, and you have been one your entire life, every second of it without interruption, and you will be one until you stop. The most examined science on earth, 300 years of it, and the thing it cannot define is the thing reading these words. I find that frightening for about 4 seconds, and then I find it hopeful, and I will tell you why. A question that is still open is a place where something can still be found. A universe that has been fully explained is a universe with nothing left in it for anyone. We are not living in that one. We are living in the one where a philosopher in Southern California looks at a puzzle grid and notices that nobody ever proved the world has a first cell. Adlam left academia for several years, incidentally. She was pessimistic about whether she could build a career doing work that unfashionable, so she went and did something else, and kept thinking, and kept publishing from outside, until enough people responded that she came back. Asked what she would tell her younger self, she said she would counsel patience, that research takes time, that you will fail many times, that many things will not go anywhere, and that you have to hang on and have faith that in the long run you will come to interesting results. It does come eventually, she said. It just takes time, which is, when you think about it, a rather beautiful thing to be told by someone who is not sure time does anything at all. So here is where I will leave you tonight. Find the cell that came first. You cannot, and you never could, and the failure is not yours. There is no first cell in a finished grid, no initial end to a bird's arc through an afternoon, no privileged moment written anywhere into the mathematics we have. There is a pattern that satisfies its constraints, and somewhere inside it there is a small warm system keeping records, which is why anything at all seems to be going by. The line does not push the bird. It never did. It is only what the flying looks like when you finally see the whole of it at once, and you're somewhere on your own line right now in the dark, wondering which end is the beginning.